Welcome, my name is Peter, and this is a joint work with my colleagues from Masaryk University, as was said. And the question we are trying to answer is relatively simple. This is ordinary RSA public key, nothing special about that. And the question is, which particular software library generated this key? And the good guess would be OpenSSL, because so many keys are generated by the OpenSSL, right? But it can't be OpenSSL. OpenSSL will never generate key like this. In fact, it was some Infineon cryptographic smart card. And how we can know this? First, because we generated that key, right? But there is a deeper reason. And the reason is that some bits of this public key are biased in a such way, so we can tell that it can be OpenSSL and it's probably Infineon smart card. But how is that possible? The public modulus is just the result of multiplication of two random primes, P and Q. So how it's possible that it's biased? And these primes are random. They are coming from some random number generator. And in case this random number generator is biased, then the primes will be biased and the modulus as well. But this is not what we do assume. We assume that the random number generator is perfectly fine and no bias there. And still the modulus is biased. And the responsible thing for this is crypto library code, which is responsible for picking the primes, P and Q. So what we did here? We first took a lot of software libraries and also 16 different cryptographic smart cards from 6 different manufacturers and asked every source to generate 1 million keys for us. At least 1 million key pairs. So we end up with a large database. It was easy for software libraries. It's harder for smart cards. Some were broken, but after a few weeks, we were able to get that amount of keys. And with this, we got both private part and the public part, primes, modulus, and we ran a lot of analysis on this. We inspected different parts. And as a result, it turned out that there are at least 7 implementation choices made by the developers of these libraries or smart cards that bias some bits in a public key. And what we can do with that? So one example, what is the implementation choice that bias something in a public key is printing the heatmap of most significant byte of primes. So we have the primes for the analysis part, and therefore we can take most significant byte from the P, most significant byte from Q, x-axis is P, y-axis is Q, and then just plot it. For every key, we will get one particle point, but because we have a million of these, we will get nice heat map. And we were really surprised by the variability we saw. This is just a few examples, but there are more. So we were surprised. But this is still about private keys. And for the classification of public keys, we don't have these. But if the most significant byte of primes is biased, then after the multiplication, of course, the modulus, most significant byte of the modulus will be biased as well. And therefore, this matters also for the public keys. This is one example. Another example is you can take RSA 512 bits, that's insecure for ordinary use, but you can inspect that. And the primes there will be half-length. And therefore, what you can do is to factorize prime -1 value. Okay? And as a result, you will get these factors. So we factorized 10,000 keys from every source by Yahoo tool. And once again, we saw different distributions. Here on the x-axis is the length of biggest factor of P-1. On the y-axis is the length of the second biggest factor. And if you have completely a random prime, a lot of random primes, you should see distribution like this one. Okay? This is expected for completely random prime. But instead, what we saw for some libraries was something like this, some gaps there. And it turns out that some libraries avoid small factors in this P-1 value. And this will, in turn, introduce some bias on smaller bits, on lower bits of public modulus. And this was, in fact, used already by Ilya Mironov to attribute some weak RSA keys to OpenSSL library before. If the library itself generates so-called FIPS primes, but there is a strict requirement that the prime value should be at least 101 bit, for example, the biggest factor of the p-1 should be at least that length, you will see completely different distribution, okay? So this is another thing that bias something in a public key. And there are more of these. So what are these 7 implementation choices? First, it's a direct manipulation of prime's highest bits. This is a very significant thing that will significantly manifest itself also in a highest bits of a public key. Another example, another factor, is the avoidance of these small factors. This will bias the small bits of public modulus, again, very significantly. Some sources, some libraries, and cryptographic smart cards requires moduli to be Blum integer, for not really a clear reason, but this is observable as well. Some libraries restrict and some don't the length of the primes, and this will in turn impact the length of the modulus as such. Some libraries do not generate primes randomly, but instead of construct these to have a strong or provable primes. And this is observable, not that significantly, but it's observable from the public modulus as well. For some smart cards, we don't know, because it's a black box for us. We don't have the code there, but it's doing something that is statistically observable. And even think like what you will do if you will generate a random value and it will turn out not to be a prime. What you will do? Will you just discard it and generate a new random value, or will you add 2 and test for the primality again? Even thing like this is observable from the public key. Just slightly, but it's observable. So when we know that there are these implementation choices that bias some bits of public modulus, we can use this for a classification. So we will start during the learning phase with a lot of keys, with over 60 million plus keys, at least million from every source. And we already know from the previous analysis which particle bits are biased in a public key. So what we can do is for every source, we can apply this mask for particle key and get particle mask value, okay? We will do this over 1 million keys and then count the frequency for different mask values. As a result, we will get some histogram. This is the example histogram for 3 different sources, and you can see that these histograms are different, okay? So we can distinguish between these 3 sources. Sometimes it will happen that 2 libraries produce the exactly same or almost same mask frequencies. And then we can distinguish between these 2 libraries, and we will group these together into same classification group, okay? What is the result of this? After going through the whole learning set, we will get a classification matrix, which contains for every possible mask value, and we are working with 9 bits, and therefore 2 up to 9 possibilities. What is the probability that particular library or group of libraries within the same group generated this mask value? Okay, and this is pre-computed from our large data set, and now we have this classification matrix. So what is the result based on this against the keys we have? We started with 38 different sources, libraries, and smart cards, and we end up with 13 classification groups. Yeah? And so some sources fell into same classification group. So why is that? So for example, here you can take a look at group 1, where you can see 2 cryptographic smart cards, same manufacturer, just different type, and most probably they just share the implementation. And therefore, we can't distinguish between these 2, and they are in the same group. Another interesting group is a group 10, where you can see 3 Microsoft libraries. Once again, we expect that the source code is same for these. But you can also see that the newest version of the Bouncy Castle is there. In that case, Bouncy Castle, the newest version, is probably not having the exactly same source, but it's biasing the public modulus in exactly the same way as the Microsoft libraries do. So it's in the same group. On the other side, what you can see here is this is just the latest version of the bouncy castle. Just the version before that is in a different group. Okay, so even the versions of the library sometimes matter if they are doing changes in the code. And this is, you can plot a dendrogram of Euclidean distances between different groups. And good thing is that we can attribute splits in this dendrogram tree to particular design choices. So it's not some machine learning black magic. We can actually attribute particular differences between groups. So now we have the classification matrix pre-computed once, so that we can do the classification. So we will take some certificate, extract the public key from that, then apply the mask of known biased bits, get the particle bit value for this particle key, and then just perform table lookup. Very fast operation. And what we will get is the vector of probabilities for different libraries or different groups of libraries. So for this particle key, it might look like this. Okay? If you have more than one key, you can get better accuracy. You can test this by yourself. We publish both datasets and these pre-computed classification matrices, but we also set up a small tool. So you can just insert your key, or you can insert URL to HTTP web server, and we will classify this one for you. So just press classify. You will get something like this, where you can see the probabilities, and you will also see which particle group is not possible. Okay, so which particle source can't generate key that you see. So this leads us to classification accuracy. So just to give you some feeling what kind of error we can have. So let's assume we have 3 different sources, and this is the distribution of mask values for these sources. If you would have 1 million of keys to classify, and you know that they are all coming from the same source, you can almost perfectly recreate this, this histogram, and then you are sure it was a green source. In this case, OpenJDK. Okay? But this is usually not the case. For learning, yes. For classification, no. For classification, you usually have just 1, maybe 5, 10 keys, but not really 1 million. Okay? So what is the situation here? We have 5 keys here, and you will take the first key, apply the mask, you will get particle mask value. And this particle mask value can be generated by all sources. Blue is most probable, but only slightly, and the red and green is possible, very possible as well. Okay? So we can have the error here. If we will add another key, this one is interesting, because this key, this mask value, is never produced by the red source, in this case OpenSSL. So we know it can be OpenSSL. It still can be a blue one, but the green one is way more probable. And as you are adding more and more key values, you are more and more sure that it was the green. So this is some basic feeling for error we have. Okay, more keys, better accuracy. So what are the actual results for the accuracy? To figure out, we set aside 10,000 keys for every source from the learning set. So set aside, so it's fresh keys, and then test it, evaluate the accuracy on that. So if you have just one key, then your most probable guess after the classification is on average correct with 40% probability. You have most probable guess out of 13 possible, and it's 40%. But on average. But there is a high variability here. For some sources, with one key, you are almost always wrong. It's less than 1%. For some sources, even one key is enough, and you are almost always right, 95%. If you are fine with a correct guess being within top 3, it's 73%. This is for one key. If you have 5 keys and you know that these 5 keys are coming from the same source, then everything is going up. The average is 78 now, and within top 3, mostly right, 97%. And if you have 10 keys, average for the top first one is 85, and almost always right within top 3. Okay, so it seems that the accuracy is reasonable. at least on the test set. So the question is, what with the real-world keys? And for that, we have very nice data set. I like to thank people that gather these large data sets. There is EPV for TLS scan with about 10 million unique RSA keys usable for us. PGP key servers data set, so you can download it. Certificate transparency database. Once again, nice data sets. There is only one issue. They are not coming annotated which particular key, which particular library generated that key, right? Obviously. But we can do at least some guesses. First of all, if you are using Apache web server, chances are high that you also use OpenSSL to generate the keys for that. If you are using IIS, then you are probably using Microsoft libraries for that. And the market share for the web servers is somehow known, so a rough estimate can be something like this. OpenSSL, 86%, 12% for the Microsoft. This is some rough estimate, okay? Something remaining for other libraries. When we took a subset of TLS dataset, where we can batch together keys which we assume that they are coming from the same source, with the size of 10, but below, at least 10, but below 100 keys. And we batched these keys based on the subject and issue date. We got result like this. Yeah? So OpenSSL 82, Microsoft slightly more than 10. So it's roughly holding. And also the blue part, this is classification for the group, which contains reasonable libraries, like Nettle, Botan, CryptLib, WolfSSL, and most importantly, OpenSSL in a FIPS mode. We can distinguish between the OpenSSL and OpenSSL in a FIPS mode. And there is also 1% remaining for formerly PolSSL, now ARM Mbit, and OpenJDK and Bouncy Castle. So this is sanity check, makes sense, a lot of assumptions, but makes sense. Better sanity check is about the impossible keys. Because we know that some sources can't generate or never generate some mask values. Okay, so let's take a look on OpenSSL and TLS dataset again. And we know that the OpenSSL will never generate keys with the mask values from this particular region. And if we will see the key from this region, we know it can't be OpenSSL. So what we can do is take all these large data sets. Big advantage is that now we can work with every single key. Yeah? We can test every single key, whether it's possibly coming from the OpenSSL or not. And these are the results. Yeah? The column with the percentage of keys that can't be OpenSSL. So let's start with the third one, which is the TLS dataset, ordinary, the internet-wide scan. And about 19% can be from OpenSSL, which leaves the rest that can be OpenSSL, and this is something that holds with the intuition we have. Even better, the Let's Encrypt. Let's Encrypt dataset is just a subset of TLS dataset, with the certification authority being a Let's Encrypt. And here, it's quite different. Only 1.8 can be from OpenSSL. And this makes perfect sense because OpenSSL is a default client for a Let's Encrypt certification client. And what about something where you don't expect OpenSSL to be used? PGP key set. You are using GPG or PGP original client, but not really OpenSSL. So it's very rare here. And here, about 47% can be from OpenSSL. And this is actually very well matching with the baseline, because if something is not used at all, it's roughly for OpenSSL 50% can be and the rest can be. Okay, so this again holds very well with the intuition we have. So we believe that works. So what is the impact of this? This is information disclosure vulnerability. So you may think about that once you are generating your key pair and publishing a public key, you are also adding a sticker saying this key was generated by that particular library, cryptics in this sense. So how you can use it and misuse it. So let's assume that some cryptographic library will turn out to be vulnerable, and because some implementation error, you can factorize its keys. but not for cheap. You need to do a lot of operations. So therefore, you can't just go through the whole TLS data set, all internet web servers, and try to factorize it, because you need to do a lot of operations. But with this information leakage vulnerability, you can just first search for the keys from this library and then factorize it afterwards. This information leakage is also decreasing your anonymity set. So if you are operating a Tor-hidden service, and for some strange reason you are not using the default client as all others, maybe because you like to protect your private keys in a secure hardware, then using this vulnerability, this information disclosure vulnerability, some Tor-hidden operators can be linked together because they are using some very, very unusual sources. Another example might be maybe you are using some cryptographic as a service server. They promise that they will generate private keys for you. They will use the private keys for you for signatures. So you can verify. You can generate a bunch of keys from their service and then ask, is it really some secure hardware or is it OpenSSL instead? And they are lying. So it can be used that direction as well. So some compliance. So this leads us to the defense. What we can do about that? So there are two lines of defenses here. First, coming from the developers of these libraries. And in principle, it's simple. They just need to unify the way how they are generating RSA keys. But this is probably very hard. I don't think this will happen soon, because at first they need to agree what is the right way to generate RSA keys. And the second thing is this is a change. This will require a change in a very critical part of code. And you will still have legacy binaries and so on. So I believe this vulnerability will stay here for longer. Fortunately, you as the users of the library can defend yourself during the generation of the keys. So what you can do is instead of generating just one key, you can generate multiple keys, let it classify, and then select the one which is least specific. Okay? And on average, you will just need 5 keys to generate. So it's practical defense. And our tool is trying to help you with that. So if you will put your public key there, we will highlight least specific key for you. So what else? In a paper, and especially in a technical report, because we work with a lot of libraries, so we have a lot of pictures. So take a look at the technical report if you are interested. We provided a summary of RSA key pair generation techniques we saw. We also analyzed random streams coming from the smart cards, and we saw some biases there. We also identified some systematic defect in generation of public keys on some smart card. Fortunately, this weak RSA key was never saw in this large data set used in a real world, which is good. And we also did some time and power analysis how the keys are generated on the smart cards. Data sets are available, so if you like to play with some machine learning on this, go ahead. So what are the limitations? I like to highlight 3. So if you have just one key, you can have lower accuracy. Okay, one key is 40% on average on our test set. For some sources, it's perfectly working, 95% probability. For some sources, is very unspecific. We can't distinguish mutually all libraries. Yeah, some libraries fit within the same group. And although we try to cover a lot of software libraries, some of these, some sources are still missing. We are working on that, most significantly HSMs. Yeah? So we still need to gather keys from HSMs. So to conclude, RSA key pair generation observably bias public keys, and different libraries bias it differently, and therefore we can distinguish this. So we can attribute based on a bunch of public keys. We can go back and say which library generated that. On average, with 10 keys, you are 85% probable, 99 with top 3. For some sources, even 1 key is enough. Yeah? You can just check the table. It's information disclosure vulnerability, so you can use it for forensics, de-anonymization, compliance testing. And it's not that easy to fix from the developer's point of view, so this will probably stay here for longer, but you can defend yourself by generating more keys. So thank you. If you have any questions, I'm happy to take it.
Hi, Kenny Patterson from Royal Holloway, University of London. Thank you very much for the very nice talk. I was wondering, when you were generating keys from smart cards, if you ever saw any repeated primes?
Repeated primes, no. We never saw that. With one example, one exception, where it was a very big key. Because it turned out that sometimes the random number generator will fail, and the smart card itself will take the failed value, which was just zeros, figure out that it's not a prime, and then will just increment by 2 and by 2 and 2, and it will end up always with the same prime. Yeah. In that case, yes, but in other cases, no. For working cards, no.
Okay, so it might be interesting to compare your results with a paper published at AsiaCrypt a few years ago where they were looking at prime generation on smart cards, and they found in some classes of cards there were repeated primes. So perhaps I think that was a Taiwanese government smart card, if I recall correctly.
Yeah, I know that paper. Yeah, but this was not the case for us. Yeah? Okay. And it was 6 different manufacturers, but yeah, we had the nice cards.
Can I ask one more question? Your classification approach is very interesting. I think it's basically an instance of Bayesian classification, but you're using a uniform prior distribution in your experiments because you have 10 million keys from each class. If you want to assess the true probability, you need to use the correct prior distribution for keys in the wild, and that's not something you can easily estimate. I wonder how that affects your classification results. Yeah,
this is a very good question. We thought about that, but the issue is that we don't know the prior probability for different groups. Yeah. So therefore, we opted to keep the prior probability exactly the same, and then see whether this will work. And then, because it matched the web server's market share, so we believe even that it works. Yeah? But this is hard to obtain the a priori probabilities. But on the other side, if you have some additional knowledge and you know these probabilities, definitely you can do better.
Okay, thank you very much.
Thank you.